Welcome back to another AP Pre-Calc lesson. We're looking at 1.5 today, polynomial functions and complex zeros. First thing we need to kind of figure out is just what is a zero. Again, more definitions, right? We really need to understand a bunch of these things before we start playing around more with arithmetic things. So zeros are known simply as a few different words. Different words you might hear is one x-intercepts. All right, that's the basic definition of a zero. You might hear the word roots. Those will be the main three you hear. You might even hear the word solution as well, but that's just a little bit different. We're going to just mainly focus on those three for now. Multiplicity is how often a root or an x-intercept or a zero actually occurs. Let's look at this function that we are given. One thing we are told in the notes is that this function is simply f of x equals negative 0.01. So negative 0.01 times x plus 4 times x plus 1 to the third and x minus 3 to the third. Well, let's start by first finding the zeros. There's two ways that you can do that. One way, you can look at the graph. We know what the x-intercepts are. The other way you can find the zeros is given this form. Right now, we're in factored form. The way I know we're in factored form is we have all of these parentheses in our equation. It's a bunch of parentheses being multiplied. Well, whenever you have your linear factors like this, one thing you can do to find the zeros, to find the x-intercepts, is you can take each of the parentheses. I can take x plus 4 and I can set that equal to 0, right? These are called zeros for a reason. It's because you set them equal to 0. It's because they are x-intercepts. Well, if we were to solve each of these, the first one we'd find is negative 4. The second one, if I set that equal to 0 and solve, I get negative 1. And the last one, go through that same process, I believe you would get positive 3. Well, what I want you to notice, when we do that, we now see those three x-intercepts on our graph. I see the negative 4, I see the negative 1, and I also see the 3. Right? There are those three x-intercepts that we just saw. Well, the other thing that we're talking about here is also the multiplicity. Multiplicity takes the exponent of your factor. Notice the exponents we have. One of them I messed up. Sorry, this last exponent was supposed to be a 2. Now notice the exponents we have. I have a 1, I have a 3, I have a 2. Well, let's look at what happens based off of those multiplicities. At x equals negative 4. Our line goes through the x-axis. Notice the multiplicity is 1. At x equals negative 1, our line goes through the x-axis. Notice your multiplicity is 3. But then when we get to this value of 2, what happens is we hit the x-axis and we bounce off of it. What we end up finding here about multiplicity. Multiplicity tells you what happens at the x-intercept. If it is even multiplicity, what's going to happen to your graph is it's going to bounce off. If you have an odd multiplicity, right? We saw 3 and 1, that is odd. What's going to happen is it's going to go through the x-axis. So if you're given a graph, you can always apply that understanding to start to create a function. You could create the factors using the reverse process of what we did, and you could create the multiplicity as well. Okay, we'll look at examples of that in just a moment. The other thing we need to know is a complex zero. The graph that we're given right now is x squared, I should have f of x, equals x squared plus 1. And notice on our graph, you don't have any real x-intercepts, right? I don't see any x-intercepts. Well, one thing we have to do is we can still use that process we just did, where we took our equation, more specifically, we took all the factors of it, and we set it equal to 0. Well, I could do the same thing here. I could set it equal to 0 and solve, right? That's a simple way to find x-intercepts. But if I do that, I get negative 1 equals x squared. We can get rid of the squared by square rooting. And now we have this weird equation because I have the square root of a negative. Well, remember, whenever you have the square root of a negative, that gives you an imaginary number. And the other thing we need to remember is if you take a square root on both sides of an equation, that also gives you plus or minus. So the negative gave us I, the square root gave us plus or minus, and the last thing we need to look at is just the 1. Well, square root of 1 is 1, so we can just have this at plus or minus I as our complex 0. The reason this is complex is you have an I. More specific, you had a square root of a negative. You had a root of a negative. Okay? Complex zeros we have to find by hand by setting them equal to 0. One thing notice, though, is we got plus or minus. That's going to tell us that complex zeros always come in pairs. All right, let's go ahead. Let's look at some more examples. First example here says, what is the multiplicity of x equals 5 when the graph shows a 5th degree polynomial with all real number roots? So we don't have any complex ones that we have to worry about. We only have the 2 that we see, right? There's only real roots, so it's only the ones we see. So it's just these 2 roots. Well, I know at x equals 5, we do not know the multiplicity, right? That's what we're trying to find. We know at x equals negative 5, they told us that spot has a multiplicity of 2. Okay, so one of them I don't know. There's my question mark. The other one is 2. The other thing they tell us is this graph shows a 5th degree polynomial. So we know that it's degree 5. Well, remember, degree is the largest exponent on your polynomial. If I have 2 different factors, x plus 5 and x minus 5, and those multiply together with their exponents, what we'd do is we'd end up adding their multiplicities to find the largest exponent. So I need to figure out what this needs to be. Well, notice at x equals 5, our line is going through it. So we know that the multiplicity must be odd. I also know that the multiplicity must add to a degree of 5. Well, what odd number with 2 adds to 5? That would be 3. 3 plus 2 gives us the degree of 5. Okay? One thing we can also do is we can be given factors. We don't even need the graph. We can create the factors and start to create an actual polynomial. For example, if I'm given the zeros 1, negative 1, 2, remember zeros means your equation is equal to that value. But we can change that to be a factor. A factor just means your equation is set equal to 0. So I could subtract the 1 over. There is one of my factors. You could do that for the other values. You could have x equals negative 1 and add the 1 over, and now you have another factor. Do that for each of these values, and you get a polynomial that looks like this. They didn't tell us about the multiplicities. They didn't tell us about what's happening at the x-intercepts. So we're just going to assume that the multiplicity at each of these is 1. So if you add all 3 of the multiplicities together, you get a degree of 3. If you try letter E then, this next problem, if you were to try this on your own, a lot of people get another degree of 3, but I get a degree of 4. Let's figure out why. Let's start by listing our factors. If I were to add the 3i over, I'd have x plus 3i. I'd have x minus 4. I'd have x minus 5. But I need you to notice something. This is a complex 0. One thing we learned about complex zeros is complex zeros always come in pairs. Well, if they give me one of the complex zeros, I need to find the other one. That is done by finding what is known as its conjugate pair. Well, right now we have negative 3 I as one of the zeros. Its conjugate pair is found by just switching the sign on the I. For example, its conjugate pair would be positive 3i. That would tell me that I have another factor to this equation, where the other factor then is x minus 3i when you subtract it over. Okay? You do need to label its conjugate pair and make sure you list it because it was another zero. They did not tell it to us, though. Each of these are a multiplicity of 1. Add them together, you get that degree of 4. Last two things we talked about in this section. B, this is kind of a reminder of one of the things we did, where you can find the rates of change, or you can find the changes in your function's values, the y values. And depending on how many times you have to find the difference for it to be constant, that is the degree of that function. We mainly did this for linear and quadratic, but we could do this for more of these problems. If I found the differences here, I'd get something like this. You could continue, right? That was the first difference. Let's look at the second difference. The second difference, I believe, is this. But again, notice it's not constant, right? First difference was not the same, so I found another. Second difference is not the same, so I find another. And when I find that third difference, now it is constant. More specifically, the third difference is constant. Okay? Because the third difference is constant, we know that this function must have a degree of 3. Sorry for the bell there. Okay, so we do know this is a degree of 3, and that's pretty simple to find. Okay, depending on how many differences you find, that does tell you the degree. Last thing we need to talk about is even versus odd. Even versus odd you can find by using this idea, plugging in a negative x to your function and seeing what happens when you get it out. The other way you can do it is by graphing. If it's symmetric over the y-axis, it is even. If it's symmetric about the origin, it is odd. What it means to be symmetric about the origin is turn your paper 180. Does it look the same? Let's look at that for the two examples they gave us. I'm going to ignore the two problems on the bottom. So on this first problem, all right, sorry for that interruption. So looking at even and odd, we start by plugging in negative x. So if I start with f of x, let's change all of the x's to a negative x. When I do that, let's just see how it simplifies. If you have a negative value raised to an even exponent, we need to know what happens there. If I raise it to an even exponent, it'll always come out positive, so that negative on the inside is not necessary. Notice the same thing for the other exponent. It's still an even. Because it's even, the negative would end up disappearing through all of that multiplication. Going through that process, notice this function is the exact same as the original. That means it is an even function. Let's look at that for odd real quick. Plug in negative x and see what happens. When we do that, a negative raised to an odd power stays negative, so you can move that negative out to the front. Same thing with the 9x. The negative to an odd power stays negative. I can move that negative in front then. The negative and the negative then makes this a positive 9x. Notice what changed in your function. G of x was x to the third minus 9x. The only thing that changed were the signs. If the only thing that changes are the signs, your function is odd. That is our 1.5 video. Let me know if you have any questions.